Hello there, my friends. For today's lab, we are going to perform a simulation. For this lab, we are going to download a software called Proteus, and here's the link for it. And of course, we will download the demonstration version. However, with that version, we cannot save our work. After downloading and installing it, just open this software and this kind of screen will appear, and click on schematic capture button. Then you will see this screen, and now component mode, pick symbol, pick button, and now let's search a resistor. Modeling primitives maybe, and here is our resistor. And now search for the transistor, modeling primitives, and NPN transistor. And now a sinusoidal source, V sine, simulator primitives, V sine. Now let's search for V source. Okay, and simulator primitives, can get it. Now let's search for the capacitor. Modeling primitives, capacitor. Now it seems everything is okay. Now click on OK button and exit from the screen. Now let's start constructing our circuitry. Let's begin with V source. Sorry, not V source. V sine. Now resistor. Now capacitor. You can rotate it clockwise or anti-clockwise directions. Now let's add another resistor. Now transistor. In order to delete this wire, right click, double right click on it, and here's another resistor. By the way, if you press X, you can turn on or turn off this alignment feature. Right click on this resistor and rotate it, right, and move it like that. Now V source, and now another capacitor. Now let's put the ground terminals. Here's the ground. Here is another ground for alignment. I pressed this button. XK, sorry. And now for negative feedback. By the way, I've just mistaken. This R2 resistor is not connected to here. Actually, it's connected to here. Sorry for that. Now for the feedback part, let's connect the base to that node. Another ground. So it seems our circuit has been constructed properly. So this resistor is for collector feedback. It satisfies the negative feedback condition. And we need a scope. From this menu we can choose oscilloscope, and for channel A let's take input, and for channel B let's take output. Now everything looks fine. What is wrong with this circuitry? The values maybe. What are the frequencies? What are the resistor values? What are the capacitor values? What are the source values? Now, in order to edit them all, we should double click on them one by one. Let's assume the amplitude is 1 volt and frequency is 10 kilohertz. You can just put K instead of typing hertz additionally, or you can just type 1 instead of 1V. That means 1 volt and 10 kilohertz. Okay. By the way, why we have chosen 10 kilohertz? Because for our circuitry it will give the maximum gain if you plot body of this circuitry. Okay, then what about this resistor? It is 5.3 kilo ohms. This capacitor is 1 microfarad. We will not change it. And this resistor is 53 kilo ohms. And this resistor will be 1 kilo ohms. And this DC source will be 12 volts. Now, what about the beta of this transistor? Now, as you can see, we can adjust beta from this text box. Let's put 60 in it and just click OK. Now let us simulate our circuit. Now here is our scope screen. It's a little bit complicated at this moment. However, we are not using channel C, channel D. We are just using channel A and channel B. Let's make these channels overlapped by double clicking on these position knobs. Double click, and let's adjust time div and lastly volt div. Now we can see the gain. And by the way, since it is AC, trigger setting will be AC, and now it seems okay. What is the gain of it? Approximately it's 1 volt peak, for peak value. 1, 2, 3, 4, 5. The gain of this circuit is approximately 5. Okay, we've just simulated our circuit. Now stop the simulation. Since you know the basics of Proteus software, let us open a pre-made project. Here's our pre-made project. By the way, we have 2 ammeters. You can add them from this frame, DC ammeter, and in order to adjust it into milliammeter or microammeter, just double click on it and display range will be milliamps or microamps. And this is our controlled current source. You can pick it from here. Arbitrary voltage controlled current source, AVCCS, and it just generates the current according to that transfer function. We will use it for our small signal analysis. And for this voltmeter, you can choose DC voltmeter, of course. Now, let us simulate all of this circuitry. Now, if you encounter with that kind of issue, if the scope does not open, then pick another scope and replace it. Now this scope seems it's not functioning. We should delete it and pick another oscilloscope. Now do the proper settings for this scope also. Okay, now it seems it's just fine. So what about the DC analysis? Okay, we can see 5.99 milliamps and 98.3 microamps from collector and base respectively. By the way, if you use that transistor 2N2369, you cannot see the beta feature of it. So in order to add another feature as beta, you should include it also. You can also use transistor model instead of a certain transistor. These values will be a little bit different because we use another kind of transistor. We use a default model, and for default model the base emitter voltage is different. So due to this issue we are getting different collector and base currents actually, but they are not that important. We are getting the approximate values. Now we know that for the small signal analysis of this circuit, we should first draw the source, and we need a R5 resistor and a base resistor and a control source. And for this control source, we know that IC is equal to GM times V pi, and we know that this V pi is the voltage across the R5 resistor, and then we need the RC resistor. Now, according to the Miller's theorem, we can break this resistor into two pieces as R1 and R2, like this. Here's our R1 and R2 according to the Miller's theorem. Now R1 is equal to RB over 1 minus AV. Now R2 is equal to AV over AV minus 1 times RB. And we know that AV is equal to V out over V input. Now we know that for this circuit the voltage gain is much bigger than 1. We can assume that R2 is equal to RB. Now we know that, this voltage is V output and this voltage is V input. Now we know that VO is equal to minus IC times RC parallel to R2. Actually, it's equals to minus IC times RC parallel to RB. Now VO is equal to minus GM times V input times RC parallel to RB. Now we know that VO over V in is equal to AV is equal to minus GM times RC parallel to RB. Since RB is much bigger than RC, AV is approximately equal to minus GM times RC. Now for the output impedance, it is RC parallel to R2. RC parallel to R2, and it is approximately RC parallel to RB. Why? Because we said R2 is approximately equal to RB. Now what about the input impedance? It is simply R1 parallel to R pi. R1 parallel to R pi. We know that R1 is equal to RB over 1 minus AV. Now, for this question, we may assume that beta is equal to 60 and Vt is equal to 26 and Vbe is approximately equal to 0.7 volts. Now we know that IB, the base current, is equal to VCC minus VBE, base emitter voltage, over RB plus beta plus 1 times RC, and accordingly IC is equal to beta times IB. Now let's put the numbers. IB is equal to 12 volts minus 0.7 volts over 53 kilo ohms plus 60 plus 1 times 1 kilo ohms. Sorry. Now we find IB as 99.12 microamps. Now IC is 60 times 99.12 microamps, and IC is equal to 5.94 milliamps. Now what about the GM? GM is equal to IC over VT is equal to 5.94 over 26, and now it is equal to 0.228 Siemens. Now for small signal analysis circuit, we know that R1 is equal to RB over 1 minus AVB. What is that AVB? Let us name this node as B, this node as E, and this node as C, and this node as E. And now let's call this voltage as VB. Now AVB is equal to V out over VB. V O over V in is equal to VO over VB times VB over V in. And we know that AVB is equal to VO over VB, we said, is equal to minus GM times RC is parallel to R2, and thus it is equal to minus GM times RC parallels to RB. And let's put the numbers. Minus 0.228 times 1 kilo ohm is parallel to 53 kilo ohms. And now AVB is equal to minus 224. Now what about R1? We said R1 is equal to RB over 1 minus AVB. And R1 is equal to 53 kilo ohms over 1 minus 224. And it is equal to 335.5 ohms. Now R phi is equal to beta over GM, and it is equal to 60 over 0.228, and thus it is equal to 263.1 ohms. What is the input impedance? It is equal to R1 is parallel to R pi, and thus it is equal to 335.5 is parallel to 263.1 ohms. And it is equal to 124.3 ohms. Now VB is equal to Z in over Z in plus RS times V in and VB over Vn is equal to Zn over Zn plus Rs is equal to 124.3 ohms over 124.3 ohms plus 5300 ohms. This is Rs. Now VO over V in is equal to VO over VB times VB over V in. We found this equation, and we found this. In here as AVB, VO over VB, and it is just equal to minus 224 times 124.3 over plus, they are in ohms, and the gain is equal to minus 5.13. And this is AB. Now let's check if we found our gain correctly or not. The scope screen is not open, as you can see. In order to open it, pause the simulation and open the digital oscilloscope. And as you can see, while the input voltage is two volts peak to peak, output voltage is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, approximately 10 volts peak to peak, and the gain of this circuit is equal to approximately 5, minus 5 actually, because if you apply the positive voltage through input, you get the negative one. And what about the base current and collector current? We found base current as approximately 99 microamps. Okay, it's a little bit different due to the model properties. Maybe this base emitter voltage is a little bit different. The modeling of this transistor can be different. For example, let us try to measure the voltage between the base and emitter. As you can see, it's not exactly 0.7 volts, a little bit different. However, it's very close. So, for small signal circuits, when we apply 1 volt, output will be minus 5.13 volts. So the gain is minus 5.13. Okay, that's all for today. Thanks for watching. Now you learned how to simulate your own circuits, and you learned to compare your results. Okay, goodbye for now.